Alrighty, welcome to the Chapter 18 video for physics class. This one is about refraction. So in the previous video we learned about ray optics, reflection, where we looked at how light bounces off of things, both flat mirrors where the angle in equals the angle out, and then also for convex and concave mirrors which have curved surfaces and have a focal point to help you determine which way the light bounces in and out. And we learned how to locate images using both the ray tracing method, where you draw lines to see where they look like they cross, and then also using the equation 1 over f equals 1 over di plus 1 over do. And so now we're going to move on and look at how light behaves when it passes through from one material into a second material, and this is called refraction. So I like this picture because it strongly demonstrates this phenomenon of refraction, where if you look at a glass tank, if you look through the top you're seeing the turtle through air, and it looks like the turtle's up here, but if you look through here you're looking through water, and it looks like the turtle's down here, and clearly there's only one turtle, but the way that the light travels from the turtle's body into your eyeball can take different paths because it bends when it passes through medium. If it didn't bend when it passed through these medium, you wouldn't be able to see the turtle in two different places, but because the light is bending and your eye does not know the light is bending, your eye just assumes it's coming in a straight line path, then your eye is going to see the image in two different places, even though they actually bent and came from the same place. Alright, so this is the same slide I had as a recap in the other lecture, so I'll do it very, very briefly. But when light interacts with small things, it can exhibit wave properties, which will be in the next chapter. When it's not exhibiting its wave properties, it acts like a particle traveling in a straight line. It can either bounce off or go through things. So what we're going to focus on in this chapter is refraction, which is when the light passes through from one material into a second material. Okay, so when light goes into a material, the light wave is actually an electric and a magnetic field that are oscillating. We're going to learn about that much later near the end of the year. But for now, just understand or accept the fact that light is made up of an electric and magnetic field. And so since matter in material is made up of atoms, it has positive and negative charge. And so the electric and magnetic fields of the light wave itself interact with the material that it's passing into. And so when it passes from one material to the other, it interacts with the material, which causes changes in the properties of the light. So the frequency stays the same, regardless of what material it's passing into. And the reason is frequency is the number of oscillations. So if you imagine passing into something else, the number of oscillations coming in has to equal the number of oscillations coming out. Now they might get bigger, they might get longer, they might get shorter and smaller, but the actual number coming in has to equal the number coming out. Otherwise, if you imagine this is like a piece of string vibrating down and then up, down and then up, if you get out more than one wave out for each wave that went in, then at some point when this string was down, you'd have an up coming out, which doesn't make any sense. So the frequency stays the same when you pass from one material to the other, but the speed and the wavelength can both change, and in fact they both decrease. So remember, the formula is the speed of light equals the wavelength times the frequency. So frequency stays the same. So if the speed decreases, then lambda, or the wavelength, also decreases. So both the wavelength and the speed will decrease when it passes from one material to the other. And here's the equation which tells you how much the speed decreases. Each material, based on how much the speed of light slows down, is given an index of refraction value. So N here stands for index of refraction. The higher the index of refraction, the more the light slows down, and then we'll see later on the more it causes the light to bend. And for a given material, the index of refraction is constant. So if you look in your book on page 486, there's a whole table. For example, like water, you should memorize, is 1.33. Glass, there's a lot of types of glass, but in general we just figure glass is around 1.5, and diamond is 2.42. So diamond has a very high index of refraction, relatively speaking. Oh, and I guess I should say air. That's kind of important. Air is, I'll put approximately equal to 1. So in a pure vacuum, the speed of light is the speed of light. So that's got an index of refraction of exactly 1.00000. In air, the index of refraction is actually like 1.001, I think. I'm not sure how many zeros are in there, but it's really, really close to 1. And so for the level of approximations that we're making in this class, you can treat air as having an index of refraction of exactly 1. And then water, glass, diamond, and any other materials. There's a lot of them listed in the table that you can look up and use. Okay, so c is the speed of light in vacuum, so that's your 3 times 10 to the 8th meters per second, which you should have already memorized. And v is the reduced velocity in that material. So for example, if the velocity of light is exactly half in the material as it was normally, then the index of refraction is 2. So the index of refraction is basically telling you what factor light slows down by. So in diamond, the speed gets cut down by more than half, etc., etc. Okay, so if we want to look in exactly at what's going on here, you can think of this light wave coming in a vacuum, n equals 1, so you have a certain wavelength. Then when you travel into the material, the wavelength gets shorter, so these two are closer together, and that's based on the index of refraction n. So the wavelength shrinks by a factor of dividing by n. Okay, so this all leads to this cool effect called refraction. So when light goes into an object, ooh, my picture's kind of blocking out some words, I apologize. When light goes into an object, one might think that it goes straight in, but as odd as it seems, that is not the case. This says, it turns out the light changes direction, bending a little bit. So here's some light rays coming in. If they're all coming in parallel, they all bend the exact same amount. The amount they bend actually depends on what angle they hit the surface. So if they're all coming in parallel, they'll all bend, but they'll bend the same amount and come out parallel in a different direction. And if you have a single source of light, it's going to emit light in all directions. So all these different directions, you can see the amount that it bends is a little bit different for each one. The steeper the angle it comes in, the more you notice that it bent. If it's coming straight through, it doesn't bend at all. So the way that we can do this, so we're going to zoom in on one particular ray, like let's zoom in on this particular ray right here, So you draw the surface flat, just like we did before. So here's our flat surface, just like a mirror, for example. You draw the normal line to the surface, again, the same thing we had before for mirrors. You draw the normal line perpendicular to the surface. Then you draw the incoming ray, angle theta 1, so incoming angle theta 1. You could also use theta in or theta incident, something like that. And then instead of bouncing off, this reflected ray is what we used to study in chapter 17. Now you can draw a ray going through but bent a little bit. And you can label theta 2 right here. And so if it went through, it would go this way without bending. So how do you know whether it bends kind of down or whether it bends up? Actually, both are possible, and the way that you can determine whether it bends down or bends up is by looking at the index of refraction of the material. So on the next slide, I'll talk about this in a lot more detail, but for now, just you can draw the ray bending and label theta 2. I mean, even if your picture is not very accurately drawn, your calculations will lead you to the right answer. So you may have your angle labeled the picture wrong, but your calculation will still be correct. So the equation that allows you to figure out this angle here as a function of this angle here is called Snell's law, named after a scientist whose last name was Snell, who did a lot of research and study on this. And he actually figured this out significantly before we understood the wave nature of light and why it happens. But it's just something that you can easily observe. You just shine a laser or even just set a pencil in water and you can look at the bent reflection. So it's very easy to trace rays without understanding why they bend. And so he figured this out, mapped it all out. And the formula is as follows. The index of refraction times sine of the angle in one medium equals the index of refraction times sine of the angle in the second medium. So n sine theta is constant. And this is very important. Remember that you're measuring the angle from the normal right here, not the angle over here from the surface. And so mathematically, as the index of refraction goes up, the sine of the angle must go down if these are going to maintain a constant value. So here you can see the index of refraction must be lower because the angle is bigger. Here the angle is smaller, so the index of refraction is higher. So what I was talking about, how do you know which way to draw this? Well, if the index of refraction is higher, the angle is going to get smaller, whereas if the index of refraction is smaller, then the angle is going to get larger. So you can tell if it's bending away or bending towards based on looking at those two values for the index of refraction. Okay? So, consequence of Snell's law. For light going from a low n value to a high n value, the angle in the first one must be bigger than the angle in 2. And so this is what you need to memorize. This is kind of your rule of thumb. The light is bending towards the normal, which means closer to the vertical line, in whichever material has a higher n value. It doesn't matter whether it's coming in or going out. let me go back a slide. This ray right now, it's coming in and it's bending towards the normal, but if you ignore this arrow here and you make it go the other way, it's coming out here this way and it's bending away from the normal because this index of refraction is a lower value, so the angle's getting bigger. So you could think of this one bending away, or you think of this one bending toward. It doesn't matter whether the ray's coming in or going out. In fact, light rays, if you have like a swimming pool, light rays are coming from outside in, but they're also going from the inside back out. So both of these things are happening. Okay, so there is a special case, because we're dealing with sine functions that have a limited domain, you can get things that are impossible, which is kind of cool. So what angle does the refracted light ray come out if we shoot light from glass into air at an angle 45 degrees? So let's draw a little picture. So let's say this is our glass, and this is our air. Here's our normal line, and we shoot the glass from the glass into the air. So we shoot the light ray is coming this way, and it says it's a 45-degree angle. The question is, where does it come out? Okay, so let's first talk about the index of refraction. Air is n equals 1, and glass is n equals, well, it's going to be, I think 1.5, sorry. Let's put 1.5. So, it's going to go from a higher index material into a lower index material, which means the angle must get bigger. So the angle is going to bend that way to get larger. So the light ray, you might say, okay, it's going to come out this way. And let's figure out what is theta out. Okay, so we use Snell's law. The angle in the air times the sine, the index of refraction of air times the sine of the angle of the air. So n1 sine theta 1 up here equals n glass sine theta glass. That's n2 sine theta 2 down here. So if you plug in, or you solve for the angle in the air, you solve for this variable here, you first have to divide by n air on both sides. Divide by n air. So then you have n air on this side, and you have all that stuff that's right here. And then to get rid of sine, you take inverse sine, so that goes to inverse sine. Anyway, if you type in all this stuff here on this side, you put in your 1.5 divided by 1 times sine 45 degrees, you get 1.06. Okay, so then you're supposed to take arc sine of that to find out this angle. But you type it in your calculator, or you just know because you took trig last year, or you're in trig this year, that the sine function, you can't take inverse sine of 1.06. It's impossible. So what that means is this light ray, it's impossible for it to come out. It can't come out. That's kind of cool. What happens if the light ray can't come out? When it hits right here, it physically is not able to get out, so instead the entire light ray reflects and stays down inside. So this phenomenon is called total internal reflection. It's a very descriptive name. The entire light beam reflects and it stays internal or inside of the material. Okay, so no light is refracted, so it must all be reflected. And again, that depends on the angle. Let me go back to the equation here. If we put in different angles of this light coming in, it's not that the light is always going to get stuck inside. It's only at certain angles. The bigger we make this angle, like if I was shooting it in from this angle or this angle, it would definitely all stay in. But if I shoot it almost perpendicular, then it's definitely going to come out. Because you know, if you shoot something straight in, it's always going to come straight out. It won't bend at all. Okay, so here's a nice little picture. If you shoot light, this is what I was just saying, straight through, it comes straight through without bending. If you shoot it at a very slight angle, it'll come out. Here's the normal line. It'll come out but bend a little bit. And then as you increase the angle that you shoot it at, it's going to increase the amount that it bends until at some critical value, it's no longer able to get out. So just before this value, like if we would have shot it right there, it would come out pretty much at like 89 degrees, right? And then if you shoot it at exactly this critical angle, it's technically coming out at 90 degrees. Like it's actually like coming out and skimming the surface, if that's even a possible way to think about the light particles. So it's a border between where the light can come out and be visible somewhere over here, and where the light can't get out and it reflects back inside. And certainly if you shine it at any angle larger than the critical angle, it gets totally internally reflected. So to find that critical angle, you just have to solve the Snell's law for when the outcoming angle is 90 degrees, because that's the boundary between when it can come out and when it can't come out. So if you plug in 90 degrees for the outbound angle, and you can solve and figure out that the critical angle that you need to shoot it at, the biggest angle that you can shoot it at before it gets stuck inside, is equal to sine inverse of n2 over n1. So sine inverse of n2 over n1 is only impossible if n2 is bigger than n1, right? So you're only going to have a critical angle when you're going from a high index of material into a lower index material. So if you were going from a lower index material into a higher index material, then there would be no critical angle. It can always get out. Okay, cool. So here's a cool little picture as well. So when you see the yellow beam, it's going through, the red beam is going through, but the blue beam, at this juncture right here, it gets totally internally reflected and stays in, and then it pops out over here. So that's kind of cool. Okay, an application which you've probably seen before is inside your swimming pool. If you're underwater and you stay at the bottom of the pool and you look upward, you can actually see this kind of cool halo effect, where you see the edge of the pool, and certainly the edge of the pool is not actually this small, because her feet are like beyond the edge of the pool. But since when you're in a swimming pool, if you look straight up, you see something that's straight out above you. But as you start looking to the side, these light rays get bent, and so for you, underwater, there's a critical angle beyond which you can't see stuff. So you see the entire 180 degree surface of everything that's outside just in this small little circle right kind of conically above you. And anything off to the side, if you look at a steeper angle, you're going to see reflections off the walls of the pool. Which is why in a pool, if you look, this stuff over here on the side, it's just like this kind of blue, weird, colory stuff. That's just the side of the pool. Whereas if you look up here, you're seeing the sky, and maybe there's a nice little palm tree or something, standing right there that you would see if it was there. Okay, let's look at image formation by refraction. Sorry. So this is kind of cool because when the light bends, that means it's taking a different path to your eye than a straight line path. And since your eyeballs always assume things travel in straight lines, what that means is the object might not actually be where it appears to be. So do you ever notice that when you look at a fish tank, the fish all seem like they're really close to the window, but then if you walk around to the side of the fish tank, you can see the fish is actually like 2 feet farther back in the tank. But when you look at it straight from the front, it's like, wow, man, it's really right here up in my business. So we're going to see why that happens. When light comes from the fish tank to the outside, it bends which way? So inside you've got all this water, that's n equals 1.33. And outside you have air, so that's n equals 1. And then maybe you've got yourself a nice little happy fish. Okay, so when the light rays are coming from the fish out, they're going from a high index of material to a low index material, which means they're going to bend which way? You tell me. Think about it, think about it, think about it. Away. Hope you got that right. So they bend away from the normal. So now the rays are bent and appear to be coming from a different place than where they actually come from. So here's a picture. So you've got the actual object back here. The light ray comes here, and I'm going to draw a little more dramatically. It bends away from the normal, so it bends away that way. And this light ray comes here, and it bends away that way. So I've just dramatized the amount that they bend. Now, if you trace these two rays, so where does it, if you're standing here looking at this light ray, it appears to be coming from back here somewhere, and this light ray appears to be coming from back here somewhere. So where they cross is where the image is, and so it appears like the object is really significantly closer than it actually is because the light diverged, and if you trace those diverging rays backwards, they're going to cross a lot closer than the actual fish. So again, I've just dramatized the location of the fish. If you don't have such a dramatic bending of the light, then the fish will look like it's right there in the picture. So this is a virtual image because it looks like the object is there, but the light rays are not actually originating from that location or passing through that location. And we can see that the image distance is less than the object distance, so it's closer here. Sorry. Because of this light bending, as I said, because of the n values. So with a plane mirror, we had the distance to the image and the object equal, but with refraction, the image is going to appear closer. All right. Okay, let's talk about dispersion and rainbows. This is a kind of very cool phenomenon that light exhibits. So it definitely is because of refraction, but it also has to do with a bit of the wave-like nature of light. So we'll talk about that real quick. So we learned that light bends when it enters a material based on the index of refraction value. But actually what happens is a little bit more complicated than that. The index of refraction, like say for glass, we say like n equals 1.5 for light. But actually for the different wavelengths of light, the index of refraction is slightly different. Not all of the different wavelengths are going to bend the same amount. And so you may have seen an experiment something like this, where you shine white light into a prism and it spreads out into its spectrum of different colors. The reason it does that is because when it passes from air into the prism and then from the prism back out into air, all of these beams bend a little bit different. It's very, very slight, but it's enough to spread out a single white light into its different colors. And that process is called dispersion, the spreading out of the light due to this variation in index of refractions. And so this is how we see rainbows. It's kind of cool, actually. In the air, there's tiny little raindrops, and then you've got some light particles passing in, and when those light particles bounce off, maybe they bounce a couple times and come off, when they pass in and when they pass out, they all bend a little bit differently. Again, when they pass in, they're going to bounce off, and they're all going to bounce off a little bit differently. And so, depending on the different wavelengths, they'll bounce out in different locations and at different angles. And so when you look up at the sky, say you're here, and you have a rainbow that's like this, if you look up a certain distance this way, you might see one color, and if you look up a certain distance this way, you might see a different color, because the light waves are bouncing out at different angles, and so they're going to, the light from a various position in the cloud is going to come to your eyeball. I'm not using good words. How can I use better words? The angle at which it's emitted is different for each wavelength, and therefore the angle at which it's visible is different for each wavelength. And so you see the striation of the rainbow. And interestingly enough, all rainbows always occur at the exact same angle. So no matter where you're standing, if you look at a rainbow, do you ever notice why there's no rainbows down near the ground or straight vertically over your head? They're always kind of at this perfect, like around 42-degree arc. This is why, because of this dispersion and the angle that they're emitted based on this kind of refraction. So it's very cool. All right, now's the perfect time to take a break. This lecture is relatively involved, and we still have to do all this ray tracing diagrams and calculations to find out where images are. So pause and take a break. Okay, welcome back from your break. We're going to learn about ray diagrams. So hopefully we can go through this a little quicker, because the ray diagrams for lenses are very similar to the ray diagrams for mirrors. There's a lot that they have in common, even though in this case light is passing through instead of bouncing back. Okay, so if your lens is thin, then the ray tracing methodology works. This is very similar to with the mirrors. We had to assume that the light rays were passing near the optical axis, not too far away from the optical axis. In this case, we need to assume that the lens is pretty thin. The thicker it is, the more the light bends while inside the lens itself, and that can throw off the calculations. So we're assuming that the light just bends once as it passes through, even though really it bends once here and then it bends again here. We're kind of combining these two bendings into one overall bending caused by the lens. So the distance it travels inside needs to be small so that we can just take those two different effects and combine them together as a single effect. So we have converging and diverging lenses, just like we had converging and diverging mirrors. And we can also call them convex or concave. Convex, again, well, actually I'll quantify this. Convex for a lens, means it's bowing out like this and bowing out like this. So it needs to be wider in the middle than it is on the ends. So interestingly enough, you can have a lens that looks like this. This is still convex because it's wide. It's more wide in the middle than it is on the end. So even though it's kind of curved away from you right here, it's curved away from you even more on this side. So the net effect of this is that it's convex. And then on the other hand, if you have concave, a concave lens is going to look like this. That's concave. Another one, a lot of times you'll see, looks like that, something like that. So convex lenses actually converge the light, which is opposite of mirrors, if you remember, and concave lenses diverge. So that's why I don't like to use the words convex and concave when talking about lenses and mirrors. I much prefer to use the words diverging and converging, because if I say a diverging mirror or a diverging lens, in your head you know that the light is going to spread out. You don't have to stop and think about, okay, what's the shape of the actual object, what's going to happen. You know right away what's going to happen. Alright, so let's get to it. Lenses have a focal point on both sides because the light is passing through from one side to the other, whereas mirrors only had a focal point on one side. So for a converging lens, you got a focal point on both sides, and here are your three rays that you can draw, three properties of this lens. Any incoming light parallel goes out through the far focal point. So it passes through and goes through the focal point over here. So this will be like our focal point on the far side. So light comes in, passes out on the far focal point. Incoming light through the near focal point goes out the far focal point. Sorry, no, I misspoke. Incoming light near focal point goes out parallel. So again, these are just opposite of each other, same thing as we had with a mirror. In the next slide, there's going to be lots of pictures, and then I'll do examples. And finally, if light comes to the center, it goes straight through in a straight line undeflected. That's because in the center, just like with a mirror, we're treating this thing as being flat. And if it's flat, then you're going to get no deflections. You only get the deflections because it's curved. Okay, so those are our three properties. Let's look at a picture that shows these three special rays. So if here's our object over here, the first one is coming in parallel to the axis, and then here's the focal point on the other side. It goes out through the focal point. The second one comes in through the focal point on this side now, and then it comes out parallel. And the third one goes straight through the middle. Okay, so they all cross right here. My drawing isn't perfect, of course. Now, the cool thing about this is that you can do the whole thing in reverse. Suppose our object was actually over here. We could have all these rays go back the other way. Suppose you came in parallel, then you would go out through this focal point. Or if you went in through this focal point, you would come out parallel. And then likewise, you can go straight through the middle again. So the object maps onto the image, but the image also maps back onto the object. So if you took this object and you moved it over here, then the image would then move over here. So they kind of reciprocate each other, which I think is kind of neat. The image location is wherever your three rays cross, same as with mirrors. But you have to note that whereas mirrors, you knew it was always going to be on one side or the other. With a lens, it could be on either side. So sometimes the light rays will cross over here. Sometimes the light rays will all be spreading out like this, and you have to trace them back and see where they cross, and that would be a virtual image. Okay. So same thing we had with mirrors. We have real images and virtual images. If the actual light rays cross, it's a real image. And if you put a cardstock there, you can see it on there, or if you put your eyeball there, you'll see it. But if you had to trace the lines backwards to see where they look like they came from, then that's going to be a virtual image, and if you put your eye or a physical piece of paper there, nothing would show up on it. So here's a little picture that illustrates a possibility for a converging lens, but a virtual image. So in parallel, out through the focal point. This one is straight through the middle. And this one is in through the focal point. So if the object is actually, here's the focal point. If the object is actually in front of the focal point, when we say in through the focal point, the light ray itself doesn't actually travel through the focal point, but it's in through the direction of the focal point. So as if it came from the focal point. So in through the focal point, out parallel. And now you can see that these three rays are never going to cross because they're actually spreading apart, diverging. So we have to trace them backwards, and then if we trace all three backwards, we can see that they cross over here. So we have an image on this side, and it's virtual because the light rays don't actually cross here. And then again, same as mirrors, we can have the image upright or inverted, whether it's right side up or upside down. And again, magnification, same formula as we had before. It's the ratio of the heights, which because of similar triangles is also the ratio of the distances. Okay. The other type of lens is a diverging lens. These lenses are thinner in the middle and thicker on the edges. And interestingly enough, I'm happy to go through it in class if you guys want, to explain why this shape of lens causes the light to spread out, and why a shape like this would cause the light to converge. Not to confuse you, but how the physical shape causes it to be diverging or converging, I'm happy to go through that. It's pretty easy to draw a diagram if you draw a nice diagram to scale and you use geometry. Okay, so the three special rays we can draw for a diverging lens are, if it's incoming parallel, it goes out as if it came from the focal point. So this light ray here, when it comes out, it diverged away. It looks like, if you trace it backwards, it looks like it came from right here. Same as this blue one. You trace it, and you trace it this way, and then if you trace it back, it looks like it came from here. So that right there is your focal point on this side of the lens. So it comes in and it diverges as if it came from here. That's your first one. Your second one says, incoming light aimed at the far focal point comes out parallel. So there's also got to be a focal point over here. So if I had a light ray incoming, aimed right at it, this way, this would come out parallel. Likewise, it's just the reverse of what we had before. If you come in parallel, you go out from the focal. If you go into the focal, out parallel. So they're just each other in reverse. And the third one is the same. The third one is the same for lenses and mirrors, both converging and diverging. If you go to the middle, you go through or bounce off, but you don't change direction at all. So in the middle, straight through. Okay, so here's some different pictures that we can get for a diverging lens. First, you just look at all these parallel rays. If they all come in parallel, they all diverge, and they all diverge as if they came from the focal point. So this is just an illustration of the first rule. This is an illustration of the second rule. Anything coming in aimed at the focal point is going to come out parallel. That's an illustration of the second rule. And anything through the middle just passes straight through undeflected. That's an illustration of the third rule. Okay, so let's take those and put them into action in a little picture. So here's our object back here. Here's our focal point right here. Let's draw our first ray in parallel, out as if it came from the focal point. So out directed along this path as if it came from the focal point. The second one is in towards the focal point. So in towards this focal point, and then out parallel. And the third one is straight through the middle. So we've got these three rays, 1, 2, and 3, and we trace them backwards to see where they came from, 1, 2, and 3, and we can see the image is located right here, right where they came from. And it's virtual here. So just like with a diverging mirror, you always have to trace the light rays back to see where they came from. Same thing for a diverging lens. It's always going to be a virtual image because the light rays are spreading out, so there's no way they're ever going to cross. And so you always have to trace them back, and it's always going to be a virtual image. Okay, let's do a couple of sample problems, just sketching it out. Find the image location and size for an object 20 centimeters away from a converging lens with a focal length 10 centimeters. So here's a converging lens. I like to draw it like this. Focal length 10 centimeters, so let's do 5. There's my focal length, and then 5, 10. There's my object. It's at 20. The focal length is at 10. And again, even though I sketch in this kind of shape, remember, all the reflections and transmissions and bending occurs on this plane. So we're treating the lens as just a single plane. We're ignoring the fact that it actually has two surfaces. We're kind of combining those together into a single effect. So let's look at our rays. Let's draw the focal point on the other side as well. So here's my focal point on the far side. Here's my focal point on the near side. So first ray is in parallel, out through the focal point. Again, because we are looking at a converging lens. The second ray is in through the focal point, out parallel. And technically you might be like saying, hey, I already know they cross right here, so can't I just say I'm done? There's my image. Technically you only need 2 rays to find the image, but the third one is always nice to confirm that you haven't made a mistake in your first 2. So I recommend, or I think you should draw 3 every time. So the third one goes through the middle, passes through undeflected, and sure enough it confirms that our answer was correct. If you only draw 2, you have a decent chance of making a mistake. If you draw all 3 and they all 3 cross, you can be very confident that you're correct. So there's our image. It's upside down. It's roughly the same size. Like in this case, it's the exact same size as the object. So it's going to be real, but it's inverted. Okay, next example. A diverging lens. So a diverging lens looks like this. Focal length, focal distance 10 centimeters again. So there's 5, 10. Focal point on this side. 5, 10, focal point on this side. The object is 5 centimeters away, so the object is located here, and we're going to draw it. 3 centimeters tall, but I don't have a scale for height. So the first light ray is going to come in parallel, and then it's going to diverge away as if it came from here. So it's along this line here. So if you trace it back like that, my ray is not very good. The second one is aimed at this focal point here. It's aimed at this one, but then it comes out parallel. And we can trace that one back. And the third one passes straight through the center. Okay, so if I trace this guy back here, and I trace this guy back here, and I trace this guy back here, you can see that these two cross right here, and this one crosses right here, and that's because I've done a pretty terrible job at drawing these rays coming out. I haven't used a ruler, I haven't lined everything up nicely. I think the answer is probably more like back there, because this one is coming out too steep. If I really draw through the focal point, wait, where am I going? It's probably coming more like that. Anyways, the illustration is fine. Here's my first one, here's my second one, here's my third one. I think the moral of the story is if you use graph paper or at least a ruler to draw these lines, you should get pretty accurate results. And if you get something fishy where the three don't line up, then double check what you're doing and making sure that you're aiming the rays in the right direction. Oh, let me say, this one is upright and virtual. Okay, sample from third. Oh, another one. Find the image location and size of a 1 centimeter object located 20 centimeters away from a converging lens. Okay, so converging lens, focal length 30. So let's go 10, 20, 30 focal length. And then here, let's go 10, 20, 30. Also, I haven't measured to make sure my focal lengths are the same on both sides, so that could also throw it off a little bit. The object is 20 centimeters away from the converging lens. So here's my object. It's 20 centimeters away. Focal length is 30. So the first ray comes in parallel. It's converging, so it comes out through the focal point. Second ray is in through the focal point. So it's in through this focal point. So in through the focal point is going to go like this, and then out parallel. And the last one is straight through the middle. So these three rays are spreading out. They're never going to cross. We should trace them back. This one's easy to trace back because it's parallel. Wow, not very good job. This one we trace back here, and this one we trace back here. And then they all appear to cross right around here. So our image is located back here. It's going to be upright, and it's going to be virtual. So I'll give you 10 cents if you can name what object or what device this is that we've just examined. Count to 10. 1, 2, 3, 4, 5, 7, 8, 9, 10. This is a magnifying glass. So you are standing over here, holding this lens, and you visibly look through the lens. And then if you put your piece of paper really close to it, in fact closer than the focal length, instead of seeing this little word right here, you see this giant word right here. Okay, so this is a magnifying glass. It keeps the image upright, and it makes it bigger. And a magnifying glass only works if you put the thing you want to see closer than the focal length. If you put it farther than the focal length, it's going to flip it upside down, actually. And that's what you can see. Take a magnifying glass, move it too far away, the object will flip upside down. Pretty cool. All right, concept question. We're nearing the end, so bear with me. You can actually take another break if you want. It wouldn't be a bad place to take a break and then come back and verify that everything is making sense. But if you don't want to, you can push through. So suppose you've got an object right here, and there's a lens right here, and the image pops out over here. So that's a lot like the first example that we did. And everything is good. You've got this whole system set up. You can see the image on maybe a piece of paper that you've set up right there, or a screen. So the question is, what happens if you cover the top half of the lens? What happens to the image? So we take a piece of cardboard, and we block out the top half of this lens. What happens to the image? Does the top half of the image disappear? Does the bottom half of the image disappear? Does the image get brighter? Is there no change in the image, or does the image get dimmer? So I want you to take a little bit of time, actually. Maybe pause the video so I don't have to sit here, but pause the video and really try to think about what happens, and when you're ready, come back. Okay, so let's take a closer look at this. If we draw our special rays, we can say, okay, this one comes in through here, and it's got to come out and map onto this point. So the focal point must be right here. Then there's a light ray that passes through the middle and also goes there. And then there's a point that goes kind of this way and then out this way. So there has to be another focal point right here. So which ray is getting blocked? Well, this one is getting blocked. So, you know, and there's a lot of other light rays that are also coming and hitting right here. There's one light ray that's going like this and then bending. There's a light ray that's going like this and bending. There's light ray going like this and bending. So there's light rays coming off in all these different directions. The fact that we only draw 3 special rays is just to help us visualize it, but it doesn't mean that those are the only rays that are actually going that way. You know, there's actually light rays coming off this way that don't hit the lens at all, and light rays coming off this way, they don't hit the lens at all. So any of them that hit this surface are getting bent and coming over here. So if you cover top half, you're going to block exactly 1/2 of all the light that's going and forming this image, but all the light rays that are coming through the bottom half of the lens, they're still going to pop out and they're still going to come over here. And so you'll have the same full image, but it will just be a little bit dimmer, exactly half as bright because half of the light is getting blocked. But you'll never cut the image in half like this, because light is coming from every particle here, from every part of the object, through every part of the lens. So if you cut off part of the lens, you're cutting off some of the light from all the places. So you'll get the whole image, but half as bright. All right, calculating size and position. So just like with the mirrors, we had the diagrams to draw, but then we also had a formula to calculate them. The super cool thing is the thin lens equation for lenses is exactly the same formula as the mirror equation. And that is super, super convenient. 1/f equals 1 over distance to the object plus 1 over distance to the image. What I've got right here is a geometric proof of this formula. So pause it and look at it if you want. But if you don't want to, you don't have to. Sign conventions are exactly the same as for mirrors, which is also super convenient. Focal length, positive if it's converging, negative if it's diverging. Object distance is always positive. Image is positive if it's real, and negative if it's virtual. So you need to memorize. I'll write this down just because it's important. You need to memorize these sign conventions, otherwise that formula is going to desert you in your time of need. And on tests or quizzes, what I recommend is calculating the value using the formula so that you know what to expect, and then draw a quick sketch using the diagram and the 3 special rays, and verify that your sketch matches up with your calculation, just so that in your head you know that you're correct. Okay, there's actually an extra section in chapter 18, it's 18.3, and it's on optical devices. So we're going to go through briefly how some of these optical devices work, because pretty much all of them are based on refraction. So let's take a closer look. First one is very simple and is something you've all used, I'm sure. It's a camera. So a camera is surprisingly simple. All you really have is a lens in the front, and it converges the light, and then you put in either a film in the old days, or in modern times an electronic detector or pixelated receiver in a digital camera, right there at the focal length or near the focal length based on how far away your object is. And so when the light comes in, it passes through this thing and it goes upside down and it creates an image right there. If you held a physical piece of paper, you would be able to see it right there on the piece of paper, and then the film just it's got photosensitive chemicals in it that when light hits it, it stores the image permanently instead of a piece of paper which does not. So to get a clear picture, you want the film to be located at exactly where the image is formed, which is not always in the same place, right? If you change the object that you're looking at, it's going to change where the image forms. So many cameras, they allow you to adjust the lens, you know, to get the image in focus. What you're actually doing is you're actually changing the length or the distance away from the lenses to the back of the camera, and that allows you to line it up so that the image is right in focus and formed right there on the surface, and you get the best picture possible. Okay, so digital cameras are kind of cool. What they have is a photosensitive back, which is actually a whole bunch of pixels. So when you talk about how many megapixels your camera is, you're talking about a mega is the SI unit for 1 million. So 1 megapixel is 1,000 by 1,000. So your resolution on your photo or your image is going to be 1,000 pixels by 1,000 pixels. So like a 4 megapixel camera is 2,000 by 2,000. So your resolution is twice as good in the X and Y directions, or 4 times as good overall. So if you have an image in a digital camera, obviously, and you look at it from far away, it looks great. But if you zoom in, you can see this kind of pixelation, and that's exactly because the light images that it's receiving are stored single pixel by single pixel. Each pixel is it sees, okay, what color do I see, and then it stores that information. This is also part of why digital picture files are so large, especially if you have a high megapixel camera. It's having to store the color seen in every single one of those millions and millions of pixels. Another important aspect of a camera is the aperture. So you have a shutter over the camera lens, and that thing is going to open and then close again. And so if you've done much photography, you know that you can change the shutter speed, or the time that it's open, or how fast it opens and closes, and that affects the brightness of your image. If you open that shutter for a long period of time, lots and lots of light is going to come in, and it's going to highly activate those pixels, or highly activate the film if it's an old-fashioned camera, making your image much brighter. And if you have a very short amount of time that it's open, it's going to open and close real quick. Only a little bit of light is going to get in, and you're going to have a much darker image. So you can use that a lot in photography to control the type of image that you capture. Okay, so we're going to also talk about the human eye, and the human eye is very, very similar to a camera. We can blink to close it, we can unblink to open it, and the light passes through our cornea and lens, which is here, and then it actually has to pass through our pupil, which is a little black hole, kind of like the opening on a camera. And then the light rays come in, and they hit the back of your eyeball, and they hit the retina, which is like a screen, kind of like a camera, but it's a screen instead of pixels or film. It's a whole bunch of little neurons, and then when the light hits it, they activate, and then they send the information to your brain so that you can see. So our normal human eyeball can focus light that's coming from really far away. Up to the closest is about 25 centimeters, which is roughly 10 inches. And so if you put something closer than 10 inches, you're not really able to focus on it, because in order to change the focal length, you have to actually change the shape of the eyeball. So when you say you get eye strain, or your eyes are tired from like reading a book or looking at a computer screen, the muscles in your eyes are actually contorting the shape of your eyeball to focus at different distances, and that gets very tiring, which is why you're always recommended to look away from the screen for 10 seconds or 20 seconds or something every so often to let your eyes rest so that they're not always focusing on close things. Okay, so just like camera lenses focus light, we can see things sharply by changing the shape of our eye. That's what I just said. The light ray, here's our lens that's focusing the light. The light rays come in and they bend together, and what you want is you want all the light rays to cross right at the back of the eyeball. But in some cases, if your eyeball is not formed well and you have vision problems, what's possible is maybe your light is being bent too much. If your light rays are being bent too much, they're actually going to cross a little bit before they get to here, and then when they actually get there and are received, they're spread back out again, and you'll see a blurry, spread out, unfocused image. So the way that you can fix this problem is that you can wear glasses that diverge light. So if before the light passes through your eyeball, it goes through a diverging glasses lens, it'll spread out a little bit, and then when your eye focuses it, it's going to focus it back in again, but since it was spread out a little bit, it will focus it right where you want it to be. So that's one problem that you might have. And so, sorry, that's nearsighted. That's called nearsighted. You can see things near, but if they're far away, your eye focuses too much. Farsighted is you can see things far away, but if things are close, your eye is not able to focus it well enough. So your eye does not bend the light rays enough. So it bends them, but only a little bit, causing the image to be formed far behind your retina. So if you wear a converging lens, it'll help your eye get some additional bending power, which will bring the image up to the retina and make it be a sharp image. So check out this picture. This is pretty cool, right? These two people are sitting next to each other, and she looks like she's like 18 times bigger than this guy. Maybe not 18, but quite a bit bigger. So she looks like maybe, if you're just watched the movie The Hobbit, she'd be a normal-sized person and he would be a hobbit, or maybe he's a normal-sized person and she's some kind of giant. Anyways, especially with film, if there's some actor who's really short and they want him to look taller, they can film things in such a way that you get your perception thrown off because you just see two things and you look at the physical size. but here's actually what's going on. One of them is closer than the other one, and so the angular size that you see when something is close, say you're standing right here, and there's another person standing right here, and then there's another person standing right here. In order to see this person, you look at that angle, and that's how big they look. In order to see this person, you look at that angle. And so what's interesting is it's called the angle subtended by the object, and the relative size of something depends on the angle that your eye has to span. So see exactly how much angle that covers, and that's how you determine the size of something. So if something subtends a larger angle, then your mind kind of interprets it as being bigger. So she subtends a larger angle than he, and therefore you think that she's bigger, but it's actually because she's closer, because she's closer, not because she's bigger. So it's easy to make optical illusions based on this kind of phenomenon. Alright, let's do a quick recap, and then we are all set and done with Chapter 18. So we learned that light slows down in materials, which causes it to decrease in wavelength, but frequency stays the same. Then we learned that light bends according to Snell's law when it travels from one material into another that has a different index of refraction. Then we learned about a special case of Snell's law, which is called total internal reflection. So if you're traveling from a high index material into a low index material, for example from water out into air, if the angle of incidence is too high, instead of traveling out into the air, it's trapped and it reflects back inside. An example of that was a swimming pool. Then we learned that curved lenses focus the light or diverge the light depending on their shape. And you can either use the ray diagrams drawing the 3 special rays to find the image location, or you can use the thin lens equation to calculate where it's going to be. And if you use the thin lens equation, then you need to make sure you take into consideration your sign conventions for the focal length, the distance to the object, and the distance to the image. And lastly, we looked at some optical devices such as cameras and the human eye. In your textbook, it actually also talks about telescopes and microscopes. You're welcome to read about that as well. Alrighty, that's all we've got for Chapter 18.